Somewhere in the universe, there exists a place with no return. Light itself, the fastest thing we know, cannot escape it. And stranger still, if a friend of yours were to fall in today, while you watched from a safe distance, you would see their time begin to slower, until it nearly stopped altogether. This isn't science fiction. It is one of the most extraordinary predictions of modern physics. This is the story of black holes, and perhaps the most unsettling truth about them is not that they devour everything. It's that we still don't truly understand what happens inside. To understand a black hole, we must first understand something quite simple. Every object with mass creates gravity. The Earth holds us to its surface. The Sun holds the planets in their orbits. But what would happen if an enormous amount of matter were compressed into an incredibly small space? Imagine this. Take the entire Earth, every mountain, every ocean, every grain of sand. Now compress it into a marble, just a few centimeters across. The mass hasn't changed, but the density has become almost incomprehensible. And the gravity? The gravity would become something beyond our ability to truly imagine. That is the fundamental principle behind the creation of a black hole. Most black holes are born when massive stars die. For millions, sometimes billions of years, a star wages a constant, silent war against its own gravity. The energy released by nuclear fusion pushes outward. Gravity pulls inward. A delicate balance, extraordinary in its patience, extraordinary in its fragility. But eventually, the fuel runs out. The star loses the energy that held everything together, and gravity wins. The entire core collapses inward upon itself. In certain extreme cases, the most massive stars, the most violent collapses, that implosion is so powerful, so total, that it gives birth to a black hole. A region of space where gravity is so immense that nothing can escape. Not dust, not gas, not light. And that is precisely why we call it a black hole. Not because it is literally a hole, but because it is perfectly, completely, utterly dark. No light escapes, none at all. It simply absorbs and gives nothing back.
But here is where it becomes rather fascinating. A black hole is not some great cosmic vacuum cleaner, hungrily consuming everything in its path. If the Sun were to suddenly become a black hole with exactly the same mass it has today, the Earth would continue orbiting it, just as it always has, quietly, steadily, unchanged. The danger is not the black hole itself. The danger is getting too close. Physicists have a name for that boundary, that point of no return. They call it the event horizon. Imagine you are rowing a boat along a river. Somewhere ahead, a vast waterfall. From a great distance, you are perfectly safe. You feel the current, yes, but you can still turn around still roll back to calmer water. But as you drift closer, the current begins to quicken. And then, at a certain point, a precise, invisible line, the water becomes too strong. No matter how hard you row, no matter how desperately you pull at those oars, you are going over. There is no coming back. The event horizon is exactly that line. Cross it, and no engine in existence is powerful enough, no rocket swift enough, no force in nature sufficient. Even light, traveling at nearly 300,000 kilometers every second, fails. It too is pulled back, swallowed, gone. And because no light can escape, no information can escape either. Everything that crosses that threshold, every particle, every signal, every secret, vanishes from the observable universe, as though it never existed at all. And that is where the mysteries begin. Suppose you are an extraordinarily brave astronaut, and you make a decision to fly directly into a black hole. What happens? Hollywood tends to show you spiraling inward, drawn into some vast churning vortex. But the reality is far stranger than anything the cinema has imagined. Because gravity does not act equally on every part of your body at once. The part of you closest to the black hole experiences a stronger pull than the part furthest away. If you were falling feet first, your feet would be pulled more powerfully than your head. At first, the difference is barely noticeable, almost nothing. But as you fall closer, that difference grows and grows until your body begins to stretch, slowly at first, then longer, thinner, longer still. The atoms that make up your bones, your blood, your breath, pulled apart, drawn out into a single, impossibly thin stream. Physicists have a name for this. They call it spaghettification, the process of being stretched like a strand of pasta. The name sounds almost whimsical, perhaps even a little amusing. But what it describes is one of the most violent ends that physics can conceive of. In the end, there is no astronaut, no body, no self. Only a thread of matter impossibly long, torn apart by gravity and drawn silently into the dark. And yet, even that is not the most unsettling part.
We tend to think of time as something fixed, reliable, constant. A second is a second, everywhere, always, for everyone. But Einstein discovered something that quietly overturns all of that. Time can slow down, and gravity is one of the forces that makes it do so. Imagine time as a river. In places where gravity is weak, far from stars, far from any great mass, the river flows at its natural pace. Steady, unhurried, even. But where gravity is immense, near a neutron star, near a black hole, The current begins to slow. The current thickens. The water moves as though reluctant. And the closer you get to a black hole, the slower that river becomes. Now, imagine you are standing at a safe distance, watching a friend fall toward a black hole. What would you see? Their clock, if you could somehow observe it, would begin to run slow. Their movements would become languid, drawn out. Their voice stretched, their signals weakening, growing dimmer with every passing moment. And then, at the very edge of the event horizon, they would appear to freeze, suspended, motionless, a figure caught at the threshold, neither entering nor leaving. From where you stand, they never truly cross that boundary.
They simply remain there, fading, like a photograph left too long in the light. But from their perspective, everything is different. They feel nothing unusual as they cross the threshold. No alarm, no warning. Perhaps not even a sense that anything has changed. They continue to fall. They pass through the event horizon. They move deeper inside. Their time feels perfectly normal to them. A second still feels like a second. Two people, the same moment, two entirely different realities. And here is the thing that makes this so remarkable. According to Einstein's theory of relativity, both of them are correct. Neither is wrong. Neither is mistaken. Reality itself is dependent on the observer. This may sound like philosophy, like abstract speculation, but it has been tested, confirmed, used. The GPS system on your telephone, the one that guides you through unfamiliar streets, has to correct for this effect every single day. The satellites in orbit experience slightly weaker gravity than we do here on the surface, which means their clocks run ever so slightly faster. If that difference were not accounted for, your position would drift by kilometers within hours. The slowing of time by gravity is not a thought experiment. It is not a theory waiting to be proven. It is happening right now, all around us, across the entire universe.
And deep within a black hole, according to our current equations, all of that matter, everything that has ever fallen in, is compressed toward a single point, what physicists call a singularity, a point of infinite density, vanishingly small, beyond measure, a place where the equations of physics simply break down. They stop making sense. They return the word infinite. And mathematics, when it returns infinity as an answer, is usually telling us something. It is telling us that our model is incomplete. In other words, science knows that something is happening there, at that impossible point, at the heart of the darkness, something profound, something real. But what precisely? We do not yet know. This is where the story becomes truly mysterious. What happens to information when something falls into a black hole? Does it vanish forever? Or is it stored somewhere in some form we don't yet understand?
Could there be a passage to another region of space, another universe entirely? Or perhaps some form of physics we have not yet discovered? Scientists are still debating. Some believe the information is encoded on the surface of the black hole itself. Others suggest it slowly leaks away as something called Hawking radiation. And others still believe we are simply missing a greater theory, one that finally unites quantum mechanics with gravity. And that is perhaps the most fascinating thing of all. A black hole is not merely an object in space. It is the place where our finest theories reach their limits, where Einstein is no longer enough, where quantum mechanics has no complete answer, a darkness not only in space, but in our understanding. Perhaps one day someone will solve it. Perhaps the questions black holes ask of us will lead to the next great revolution in science. But for now, somewhere between the distant galaxies, black holes continue their silent existence, bending space, slowing time, and keeping the deepest secrets of the universe entirely to themselves.